Hi, my name is Alexander Purchell, 221-420-088, and this is my assignment number 6 for dynamics. So let's just get the camera set up here as best we can. Okay, so we have the following setup of a wheelchair with lots of information given. We're given the dimensions of this bar AB, we're given the radius of the wheel, we're given the angular velocity, we're given the radius of gyration, the mass of the wheel, and the coefficient of static friction. So what we need to start with in this question is finding the moment of inertia, and that's equal to the mass times the radius of gyration squared. We get this value 0.5625. Then we're going to make a series of 3 equations. It's going to be the sum of forces in the y direction, the sum of forces in the x direction, and the sum of moments about b. So just to point out a few little things here, the 3/5 and the 4/5 is because it's a 3, 4, 5 is the hypotenuse from A to B triangle. And so the 3/5 and the 4/5 is the multiplier we put on to basically break it into x and y components. And then for the moments about B, it's the moment of inertia times the angular acceleration. And then when we solve all these equations, the system of equations 1, 2, 3, we get the following results: that FAB is equal to 111.48 newtons. The normal force at C is equal to 178.4 newtons. That the angular well, I suppose it's deceleration because it's negative of the wheel is negative 31.7 radians per second squared. So then we want to find, the questions asking us originally to find the reactions at point A in the x and y directions. So we have 4/5 FAB equal to 89.2 newtons reaction in the x direction, which is acting to the left, because the force of friction, static friction, is acting to the right to try to resist the tendency of the wheel to slip towards the left. We find then that the reactions in the y, the reactions which are pointed upwards, are equal to 66.9 newtons. Then we're going to find the time it takes for the wheel to come to a stop. We have this simple kinematic equation. We saw a similar one in like rectilinear kinematics, but just you swap out rectilinear velocity and rectilinear acceleration for angular velocity, angular acceleration. We plug in our numbers, 0 because we're finding at the time it takes to stop, and so obviously the velocity at the moment that the wheel has stopped is 0. We get that the time takes for the wheel to stop is 1.26 seconds. Now finally, for part B, it asks for some design considerations to make the wheelchair more ergonomic, more functional. I came with 3 things. The first is for softer tires, or wheels I should say, if possible to use maybe like I don't know if they would maybe be using plastic, maybe to switch that out for some kind of rubber. The reason I would think for this is that, you know, if somebody's rolling around in a wheelchair and they're bumping over some stuff, they would want to have that impact kind of cushioned better. And if you have a softer material for the wheels, you would get better cushioning. The second is a lightweight frame, because if you have a user that's wheelchair independent enough to push themselves around, then they would still benefit from having a lighter frame to be able to push themselves better. And if not, the caregiver assigned to them would obviously want a lightweight frame to be able to push around better. And the last thing I said is larger wheels. And the reason I came up with this was to be able to roll over obstacles better, which you might get lots of, whether it's in the home or the hospital. So these are my 3 considerations. Part A was shown previously. Thank you very much.